All right. So it's 10 a.m. First things first, does anybody know a person by the name of John Forrest? No?
I do.
You do?
I mean, I don't like personally know him, but he lives down the hall from me.
Um,
Another section.
he's another section.
Yeah,
He's
like
in my hallway, I believe.
He's in your hallway. No one's personal friends. No one can text him, tell him how to get on.
I have his number actually. I can text him.
All right, because Tommy needs to be in this class. He joined late, so that's why we're still dealing with this. Thank you, guys. I appreciate it. All right. So, looks like everybody has returned except for, I guess, a few commuters. Remember, guys, keep your cameras on. I don't like talking to a blank screen. It's not fun. All right. So how'd it go getting back onto campus? Any issues? Any problems?
Besides the COVID test.
You all good? All right. So let's talk through a couple of things first. As for quizzes, you should receive your grades about half an hour after you start, so that'll give time for everybody to finish it in the class. All right. If you have not seen your grade, let me know. I might have misclicked something. It doesn't really let me see exactly what it shows on your end. So going from there, quizzes, we will go over them once everybody has completed it. All right, so if people have missed it due to actual reasons, like I have someone in another class who had drill and they couldn't attend the class, so they're going to be doing the quiz today. So it's one of those things, we'll review the quiz before the actual test, but after everybody has completed it. All right. Just a reminder, we have a quiz at the end of class, so just remind me at the last 15 minutes. That's on piping. All right. And we are going to be going into in-person come Monday. All right. There we go. All right. So we are going to not be on Zoom past this. Okay. If you get tested positive for coronavirus, I need to know as soon as possible. I know you guys get tested Wednesday, right? Correct?
Yeah, today and tomorrow.
Tuesdays and Wednesdays.
Yesterday and today.
Yesterday and today. All right. As soon as possible. I know I will receive the email that you're going to be in a health screening or whatever they HIPAA, do to it. Just make sure I know about it so that way I can deal with it as quick as possible. All right. The more information you guys give me, the faster, the faster I can react to it and make this all easier so you guys don't miss the lesson or what have you. Okay. So if you test positive and you can't attend class in person on Monday, we'll deal with it. You'll get an email from me as long as you email me first. All right. So we'll discuss more about that come Monday and all those other fun things. So Monday also begins 5:40 lab. All right. So Monday is lab. All right. So lab starts the 25th. All right. So if you have physical lab, which you all should, you have to start attending. All right. Miss one of those, you fail the class. All right. Remember that. So what you need, it's going to be attending on the ship. All right. You're going to basically be going over things that we learn in class. All right. You're going to be physically putting your hands on it. That's what lab is all about. Pulling up the schedule now. All right. So just an example, the first week is going to be basically you're going to draw out the engine room. You're going to get a sheet of paper with it that you're going to label everything in the engine room, all that kind of good stuff. You're going to get the safety orientation, things like that. All right. Now, where are you going to meet? You're going to meet right directly on the gangway. All right. So right at the gangway is your meeting spot for the first week. All right. After that, you're going to meet where your lab instructor informs you to meet. So sometimes it might be reefer flats. All right. Sometimes it might be steering gear, but they will tell you from week to week where you're going to be meeting the next week. All right. So the first week, you're going to meet at the gangway. All right. Make sure you bring your TWIC card so you can get onto the ship. All right. The other things that you're going to need is, all right, you're going to have to be in your boiler suit. You're going to have to be in your boots. You're going to have to bring pen, any sort of paper that you want to write on. So if you want to take notes, bring paper. All right. I recommend some sort of like a clipboard of sorts, something that you could write on. There's not a lot of surfaces. There's not a lot of desk in the engine room. All right. So bring something lightweight that you want to be able to write on. All right. Gloves are always handy to have in case you have to go through with something. And then I would recommend earplugs because the ship is in a working condition right now. It's not physically, on, but the maintenance that's going on is pretty extensive. So make sure you protect your ears. All right. So earplugs are pretty much a must. All right. Also, that going from there, we are in like I said, a working condition. So you have to be ultra aware of your surroundings. All right. There's going to be deck plates that are going to be up. Don't be walking backwards. All right. Always be aware of what's happening around you. It's probably in a little bit more of a chaotic state than even what's going on than if we were actually out at sea. All right. So being in shipyard, things are just going to be different from day to day. All right. So you may be walking around on, the deck plate and all of a sudden you just fall through the deck plate because there's no deck plate there that day. And there's also an opening to the tank that's below it and you fall right into the tank. All right. That's a lot of paperwork for me. You get injured. You can't go on summer sea term. Not fun. Okay. So be aware of your surroundings. All right. There's going to be not me teaching the lab. It's going to be first class lab instructors, going to be about 4 per depending. The only exception to that rule is, let me see. The only exception to that is Tuesday at 9. You have 3 because there's only 11 of you. Same with Thursday. Thursday at 9, you guys are the lucky ones. There's only 6 of you in that class. So you're pretty much getting a one-on-one. You have 2 instructors. Everyone else, you're pretty much maxed out. So, all right. Now, you'll find out who your lab instructors are. They're going to be first class. All right. A lot of them are going to have repeats, everything like that. Any questions about lab before we continue on? No? All right.
Professor,
Last thing is that the plate tracing, all right, that's going to be basically talked in depth the week of February 8th, all right, just so that you're aware. Okay, going from there, let us go into pumps. Does anybody have any last minute questions on piping? All right, because we're not going to finish pumps in today. Guaranteed. Last minute questions. Nope. Okay, let's get going. All right. So, pumps. All right, we're going to be doing pumping basics, centrifugal pumps, positive displacement pumps. All right, these are your 2 main types of pumps. centrifugal and positive displacement. All right, we're going to hit centrifugal first and then go into positive displacement pumps. All right, so pumps deliver energy in foot-pounds, pound-inch, joules, etc., any unit of energy to a given volume. So cubic inch, cc, gallons, all right, liters. All right, it's usually thought as a force over an area, but it's also an energy per volume. All right, so that's how we get PSI. All right, so you're going to always be looking at this and seeing what the pressure is coming out of a pump. All right. So energy gained per unit volume. All right, pounds per square inch, or PSI. So pressure times flow is power. All right, energy over volume times volume over time is equal to horsepower. So we have PSI times gallons per minute over 1714. All right, that's just an arbitrary number, basically. We get horsepower. That's 1714 is just one of those units that, because it's the imperial units, we have to do that. All right. If we look over here, we just have pascals times meter cubed per second is equal to watts. All right. Watts is the same thing as our horsepower. It's just an SI. All right. So we have something called head. Head energy per pound of liquid, commonly expressed in feet, representing the vertical height of a static column of liquid, corresponding to the pressure of the fluid at the point in question. That's a lot, right? So we'll go over it, don't worry. In general, a liquid may have three kinds of energy. That is the capacity to do work maybe due to three different factors. All right. We have potential head, which is the energy of the position, the work obtaining and dropping a vertical distance. All right. And then we have static pressure head, energy per pound due to pressure, the height to which a liquid can be raised by a given pressure. Then we have velocity head, or kinetic energy per pound, the vertical distance a liquid would have to fall to acquire velocity. All right. So we can look at this and see that each different type of liquid out there will have a different type of head. All right. If everything is under 1 PSI, we could see that the column of liquid that's pushed up under 1 PSI is going to be different, all right, between water, gasoline, and molasses, all due to their specific gravity. All right. So, and then that's our velocity head. How far does something have to fall? The vertical distance a liquid would have to fall to acquire velocity. All right. Then we have static pressure head, which is down here. That's all static. And then we have potential. All right. The work it's going to obtain by dropping that vertical height. All right. So if you hold a glass of water higher above the desk, it has a potential head. All right. So total pump head is the difference between the energy per pound on the discharge side versus the suction side at a pump. All right, so this is a centrifugal pump right here. You could see it as the symbol that it's drawing right here, or we also use this symbol, which is a lot easier to draw, and it means the same thing. So you don't have to draw this exactly. Just drawing this will mean the same thing. All right. Going from there, this in the center, we'll hit this in depth in a few seconds, is our suction. All right. And over here is our discharge. All right, and this is for a centrifugal pump. So we take the center line of our suction. All right, it's right in the middle versus the discharge side. All right. So the suction side of the pump expressed in feet, ZS and ZD, are the elevation in feet to the point of suction or discharge measured from the datum plane, so basically the center, and the inlet port. All right. So we have ZS, which is going from where we're taking our pressure. All right. And we go to ZD, which is also where we're taking our pressure on a discharge. And those distance in height. Again, don't care about that. HFS and HFD are friction losses in feet in the direction of flow from the pump suction and the discharge ports of representative measuring points. All right, so basically all HFS and HFD is just line loss. All right, it's the pressure that you're going to lose over the distance of certain piping, all right, because of the friction inside the piping. All right, no piping is going to be frictionless of what's happening, all right? So most of the times you can negate that and not think about it. But there is certain times where you will have to, as an engineer who is going to be an operator, will have to deal with this, all right? So I was in dry dock with one of my vessels. We had to keep our AC unit in our control room running, not for our engineering comfort, but because we had very sensitive electronics. All right. Modern ships are very, very sensitive. It's almost just basically your control room is AC because it's just a giant computer. All right. And it needs a lot of cooling. And if it was just left to be in the engine room, it would just destroy it. So because we're in dry dock, we get our cooling from the water. Well, we're in dry dock, there's no water around us. So we still had to get cooling to our AC units. We had to basically, if you're in the dry dock, and we were in one of those raising dry docks, all right? So the water line was down here, and we're in the dry dock here. We had to basically run a freshwater hose from the dry dock all the way over here. It would loop down, came up, and then went way down into our belly into the engine room. And it was a garden hose. It was about 10 of them. So we had to get a certain amount of pressure into our AC unit. All right. Too much pressure, we would destroy our air conditioning unit, and we would have more problems than what we started off with. All right. Too little pressure, and it wouldn't get enough cooling. So we had to monitor, we had to have someone on a radio all the way here on the top of the dry dock. We had to have someone here because the ship was so deep that the radio wouldn't penetrate. And then we had to have someone down here who was actually monitoring the pressure before it was going into the AC unit. I forget off the top of my head what it was, but let's just say it needed to be 60 PSI of water pressure. We had to have almost double the water pressure all the way at position 1 because of that much line loss. That much friction was being generated just by the fact that it was a long garden hose. And that's when you have to care about line loss. We didn't pull out any calculators or anything, but what we did do is we sat there and we slowly opened up the valve at position 1 until at position 3 we had 60 PSI. All right. That's what you have to pay attention to, line loss, because we didn't at first. We spent a couple of days, admittedly, we kept a couple of days keeping position 1 exactly at 60, and we were getting a trickle of water coming out at 3 because we didn't recognize how much line loss would be going on. All right. So that's when it's important to pay attention to what's going on around you. All right. So pump types, we're going to be going off of kinetic, versus positive displacement. All right. And like I said before, it's basically centrifugal versus positive displacement. All right. The technical name for centrifugal is a kinetic type. All right. Just how a throttle valve is the type for a butterfly valve. All right. Would be the butterfly valve. This would be called throttling. All right. It's the same thing. Kinetic is what its function is. Centrifugal is what the actual type is. Okay. So both centrifugal and a special effect are both kinetic type pumps. All right. So a jet pump is a special type. All right. So inside centrifugal, we have all these different types. We have radial, we have axial, and we have a mixed flow. Most of the time, you will see a radial pump. All right. And then you'll see jet pumps in a very specific type of the industry. All right. And that's in dredging. So centrifugal is a radial flow. Again, it uses the symbol that we showed earlier, this type of symbol. All right. We have something called the impeller. We have the eye, which is our suction port. We have our volute. All right. And then over here, it doesn't say, but this is our discharge. All right. Now, notice the way it's spinning. All right. It's spinning in this direction. All right. It follows the volute around as the volute increases in size. Now, if you think about it, you would think that it would want to be this way, right? Because the vanes are pointed in that direction. It has like an arch to it. All right. But if that were the case, it would just be grabbing. It wouldn't be flinging. It wouldn't be imparting its energy onto it. It would just be grabbing it. All right. So what's happening is it's these vanes are almost like flinging it and building up pressure as it goes around. All right. So that is the direction. These vanes are going to go in this direction. All right. And that goes for any centrifugal pump out there. All right. So it will flow whatever liquid you're going in that direction there. So moving forward, we can go horizontal or vertical. All right. We have different types of impeller constructions. Now, if we're in a horizontal position here, you could see that this is our suction and this is our discharge, right? Pretty easy to see. But over here, could you tell is easy? No, you'd pretty much have to crawl underneath and really take a look at it. All right. Or it'd have to be labeled. We can kind of tell on this one because it's really shown in the drawing. But if you look, this one over here dives down into the center, and this one over here comes out and is almost enlarged on this side. All right, so this is going to be our discharge, and this will be our suction. All right, so you just have to know the basics that the eye is the suction. All right, know the construction isn't going to really change. You're still going to have a skinny part, and then it's going to be a larger volute over there on our discharge, no matter what. So look for that. And you can see this side has a larger volute where it's skinnier over here. This must be our discharge. All right. Just use the clues. Look around. It's not always going to be a labeled, simple arrow pointed in the direction that you think it's going to go. All right. Now, our impellers have different types of construction. All right. Basically 3. We have a closed impeller. So the vanes are enclosed inside a space. All right. There's a flat panel on both sides, and that would be considered a closed. We have an open impeller, and then we have a semi-open. All right. Now, these semi-opens, you can kind of see that the vanes end pretty early. They don't continue all the way around. Like this one has a pretty much an open circle, where this one has almost like a star pattern to it, where you can see these veins are ending quite earlier. All right. And they just have different pros and cons of what they use, but that's more on the design side of what's happening. Pretty much if you're going to be in operations like we are all training to do, whatever comes out, put it right back in. Buy the part that comes out of here. All right, don't try and reinvent the wheel. There will be a data plate. You'll go to your computer. It'll spit out the information of what you need. And then you order that part and you hope to God that the person ordering your actual physical parts doesn't mess up. And all of a sudden you end up with toothpaste instead of a impeller. Not a true story, but it pretty much gets that ridiculous. All right, so now we have single suction. All right, so single suction, we only have one location where we're going to be pulling a suction from. All right, it looks like it's going to be having a double discharge, but that's not correct. Remember, it's going to be spinning in a circle. We're going to have that volute that's going to be around. All right. Now we have a double suction. So that means on both sides of the impeller, we will be sucking in fluid. All right. Again, we're not having a double discharge here. We have that volute all the way around. And then we have something called a multi-stage. All right, a multi-stage will basically have one centrifugal pump after another, all right, in succession. All right, it'll go from one into an eye, come out, go back into an eye, come out, go back into an eye, come out, go back into an eye, and then finally discharge out. All right. Now, we're going to talk into pump characteristics. So we're using a chart here. Our y-axis is pressure. Our x-axis is flow in gallons per minute. All right. And pay attention to what's happening up here. All right. So, of course, with anything, we know we have an ideal line. All right. What our math tells us should happen. But then we have our line in actuality, what the real world will show us. All right. And what's showing is right here, as we are going to stay steady state in our pressure, technically, right? We're going to slowly increase our gallons per minute. But in reality, the more we increase our gallons per minute, we are actually going to fall off and will reduce our pressure, right? So the more gallons per minute we're going to be seeking after over here, the less pressure we'll have. All right, we can actually see that line is a little off. And let me switch to something that will stand out. So we'll go green. All right. So then we have our system characteristic line. All right, so this is our actual system characteristic. And then like anything in the world of engineering, we're going to follow our chart. All right, so you stick one finger on this line, you follow it until you stick your finger on this line and those two fingers meet up. All right, it's like any other table chart out there. You're going to go and follow it until they connect. All right. And the reason for that is because we're using our pumps characteristic line and we're using our systems characteristic line. Just because our pump can exist over here doesn't mean that our system can take it. All right. we may not have a large enough pipe on the outlet that can take that amount of gallons per minute all the way over here. All right. So we are going to operate here for this system. All right. There we go. So if you look, if we enlarge the system, if we go from, say, a 2-inch pipe to a 4-inch pipe, well, now we can operate over here. All right. So we increase our pipe size. We went from a pipe size that was all the way down here and restrictive to something that's more free flowing. All right. So pay attention up here as when you're looking at it for your own. And if we widen this pipe all the way to its pretty much max, all right, it will exist all the way down here. All right, since we're reducing the amount of friction, we're opening the pipe, we're making the pipe, we're getting rid of our restrictions. We're basically letting this pump run at full tilt. All right. So as we go and we get smaller and smaller pipes, we're going to have smaller and smaller amount of flow. We're going to have a greater pressure though each and every time. All right, the pressure all the way down here at position 1 is going to be less than the pressure over here at position 2, even though our trade-off is more gallons per minute. All right, so it all depends what you're seeking after. All right, then we finally get back to that position. We can see we get very restrictive. All right. Now, if we go extremely restrictive, we can see that this is like, say, like a 1-inch piece of pipe. All right. We're getting more close to our ideal pressure, but we have very little gallons per minute. All right. Now, this is shut-off head. All right. What's happening here is this is a closed valve. All right. There's a blockage. The system is completely done. All right. There is no flow. We have our maxed out pressure for our pump, and there is a no flow scenario. Right. Look at our flow down here. All right. We are at 0 on the x-axis. Now, what would happen to the pump if we're in a no flow scenario? What happens? Does it explode? Does the ship blow up? You lose your job, you're fired? What happens? Anything from nothing to full failure. What are our guesses? We are imparting a kinetic energy into this, right? We are in a no flow scenario. We are at 0 gallons per minute. If I left this for 5 minutes, what would be happening?
It would tear itself apart.
After 5 minutes, it wouldn't tear itself apart. All right, even a couple hours, you would have problems, but it wouldn't tear itself apart. All right, think about what's happening here. Just because we have pressure, right? We are at our max ideal pressure here, right? But we're in a no flow. So there's nothing being added into this spot right here. Nothing's going into our gallons per minute. There's nothing going to be building up, all right? It will sit in its ideal pump characteristic. It will never go above. All right, because like we said, we follow our blue line and we follow our red line. It just so happens that they meet right here. It will never increase above our pump. Now, eventually, you're right, this will break. All right, because we're inflicting, we're pushing kinetic energy into this, right? It's a type of energy. So if we're pumping water, just pure water, if you let this run for days, you would boil the water off in here because the amount of energy you would put into it, it would heat up and it would boil. All right. And you would break your pump. You would burn up your pump in that way. But in all technicality, this is how you're supposed to start up a centrifugal pump. All right. With a shut off head scenario. And then you slowly open it to where it's supposed to be. All right. So again, think about it. We are in our no flow scenario. We're not adding any more gallons per minute. There's nothing being added into it. All the liquid that is there will be the liquid that's there. All right. We're in a zero flow. We just have a lot of pressure. All right. Thank you for being the only person that took a guess on it, though. So again, as we open it back up and we turn to normal operating pressure, all right, and flow, that's where we will exist. If you understand what's happening here, all right, on this chart, you'll understand these pumps without failure. All right, there'll be no guess of what's going to happen. This is kind of like the earth science chart. All right. If you can figure that out, pretty much all answers to a centrifugal pump leads from this chart. All right. You will understand that this will be in a no flow scenario because of its gallons per minute, everything like that. So if we increase our RPM, we will have now a higher pressure, and it will come with its own ideal line, but we'll stick to our actuality. Just by increasing our RPM, we will get a higher pressure with a slightly higher flow. All right, the distance from here to here is not much. But the distance from here to here is a lot greater. All right. So when you're increasing your RPM on a centrifugal pump, you're looking for an increase in pressure, not so much gallons per minute. The gallons per minute is kind of just an added bonus. It won't be many, unless, of course, you're going from like here to here. All right. What you're really seeking after is that pressure. Because even if you're going from line 1 to line 2, look at that pressure difference that you would have. You would only have a slight increase in gallons per minute, right? What you're really seeking after is that RPM, that pressure. All right? And again, as you increase your pipe size, follow your pump characteristics, it will stay on that pump characteristic line, and it will stay on that system characteristic line. All right, and as we dive way down, we have lower RPM. We're gonna have a lower pressure, lower flow, all right? And still, same position. We're still gonna have shut off head at that spot, no matter what happens, all right? Any questions on this before we continue?
I have
Okay.
a question.
Yep.
Does the ideal always stay the same, or does it vary like with the different types of pumps?
So the ideal line, this is a centrifugal pump characteristic chart for whatever specific pump this is. Whatever brand, everything like that. You will get this chart basically with all of your pumps. All right. So this ideal line is very specific to the physical pump that you're looking at. All right. And then your actual line is going to be whatever speed you're going to be running your pump at. All right. So the ideal, like we said, is the calculated value it should be running. but the actual is what it will run in real world testing. All right.
Okay.
Anybody else any questions? All right. From there, we're going to positive displacement. All right. Again, these are the two big different ones. All right. Kinetic or centrifugal versus positive displacement. Now, inside positive displacement, we have reciprocating and rotary. Inside reciprocating, these are two different types that we're going to be seeing animated through this. All right. So in reciprocating, a fixed volume, and that's the big thing. This is positive displacement. It's a fixed volume is pushed through with each stroke. All right. And a revolution or a rotary, every single time it spins, again, a specific volume. All right. It's a fixed volume. We're going to go right into a pump curve on it. All right. Now, positive displacement pumps. Knowing that a fixed volume comes from them, what would be considered a positive displacement pump in your house? Everybody would have one, at least, I hope. I really hope you have this, that I'm thinking at least. A fixed volume, no matter what happens, environmental conditions, anything. What is something that would be considered a fixed volume pump, a positive displacement pump in your home, everyday use? This isn't like in your boiler or anything like that.
Would it be in your shower?
What would it be in your shower?
Because it's usually like, it's always like a consistent flow, like a consistent pressure.
All right, so that, depending on where you live in the world, is going to be based on a head pressure. All right, so if you're out on the island in the suburbs, you have those water towers. Those go down into that, and then sometimes you'll have a hot water circulating pump. That's actually centrifugal. All right, so that's going to be a constant pressure. All right.
In the toilet?
Toilets, again, is going to be, that's based on a type of siphon. All right. So that's how toilets work, where they have their flow. Good guess. All right. What else? What would be a fixed volume? Every single time you use this, the same volume of fluid comes out, no matter what, on each stroke or each rotation.
A sink?
Same thing, the sink is going to act like a shower. It will be, depending on location, going to be based on head pressure or a centrifugal pump in your basement.
Like gas.
So a gasoline pump?
Yeah, like the stove.
Oh, the stove. So that one's just based on, if you're using that's just based on pressure back to wherever you're getting it. All right, you're gonna have a regulator, things like that. All right, so if you have a propane stove, it's going to be based on the pressure in the tank. If you're gas and hook up on gas, it's going to be the pressure back at the facility. These are good guesses. What else could be utilizing a fixed volume?
Your fridge water?
It's the same thing. It's going to be based on head pressure. Whether if you're in New York City, you have the water towers all the way at the top of the building, or if you're in the suburbs, you have a water tower in your neighborhood, or if you're off of a well, you would be utilizing a well pump with some sort of pressure tank.
Air conditioning.
Air conditioning. So that utilizes a compressor. All right. And that every time will utilize a suction and discharge of the same volume. All right. But the simplest version out there is just a perfume bottle, a soap dispenser. This is a glasses cleaner. All right. So every single time I press down on the top of this thing, I will be not wasting it. I'm going to basically spritz, and I'm going to get the same volume no matter what. I'm not having to sit here and spin a little wheel, right? I'm going to have to sit here and crank something up to get a centrifugal pump going, right? I'm not going to have this. This doesn't have a little gear ratio in here where as I push down, it spins a little centrifugal pump. It's a positive displacement pump in this. All right. Every time I spritz this, I get the same volume of fluid coming out. Granted, it's aerosoled, but it's the same volume. Same with a soap dispenser, right? If we have a soap dispenser and we go up to it on our, and we pump it up with our hand, that is a positive displacement pump. Okay, it's a very basic one. It's a throwaway one, but it still exists as a positive displacement. All right. How about those long water guns? All right, the ones that you pull back and it's basically a long syringe, right? Is that a positive displacement pump?
Yes.
Yes.
Yes, because every single time you suck it up and you pull, you're pulling a fixed volume of water, right? And then as you push it out and you're pushing the two ends together, it's a fixed volume that now gets jettisoned at whoever you're going to be putting this water at. All right. These are all positive displacement pumps. They don't have to just look as a giant piece of machinery. They come in all different shapes and sizes. All right. Now, the benefits of a positive displacement pump over a centrifugal. All right. Positive displacement is called self-priming. All right. Does anybody know what the word priming means in the world of pumps?
Isn't it like you have to introduce some kind of energy into the system to start it?
So you're close. All right. What's basically happening is when you can self-prime, all right, think about when you buy a brand new bottle of, if you use a pump for shampoo, or this is brand new, or soap, what have you. When you do those first couple of squirts, when you do those first couple of pumps with a shampoo bottle or a soap, does anything come out?
No.
It seems like no, right? Because you're looking for soap, right? You're looking for glass cleaner. But in reality, if you were to really look at it, you're removing air, right? That is a fluid. So every time it's a fixed volume. But as you go, I'm going to draw it right here. So that is going to be the top of the spritz container. All right. Everybody see my soap bottle?
Yes.
All right, good. So every time you move a fluid, right, this is filled with whatever is going on in here. All right, let's call it soap. And you buy it for the first time. And that is filled with that liquid. But the straw is filled with air. So every single time you do one pump, you're going to move a fluid. And that fluid is just air this time. All right. Yes, we're not receiving anything in here, but it takes a couple of pumps, right? You have to pump it like 3 or 4 times before you actually get a little bit of fluid. And then you get that little like burp of air, right? So what's happening is every time you do one pump, all right, you removed a volume of fluid here. All right. So let's call it that much right there. Oops. Don't know what I'm. All right. And then you do your second pump. Well, now this is still at that position. It's going to remove the same volume of air. So now that fluid is there. All right. The third pump, it goes to here. The fourth pump, it ends up somewhere in here. The fifth, and now like we're at the sixth up here. Finally, at that last one, you get that weird gurgle of fluid. All right. And that's the main difference here between a self-priming pump, a positive displacement pump, versus a centrifugal pump. All right. So self-priming means is that when we started out, we had no fluid in the pump, right? Because the pump is in like this vicinity, correct? If we take a look at it, the spring area is up in there, right? It's not all the way down here below the fluid. That's just the straw, correct?
Correct.
So if we look at a centrifugal pump with its eye and the vanes, all right, we'll put our discharge over here. My lovely drawing. All right, if we turn this on with just air in there, are we going to be able to draw a suction? Are we going to
No.
be able to prime? No. And that's why, Nicholas, you were the one who was saying imparting an energy, right?
Yeah.
All right. So that's why I was saying you were close. All right. We're imparting an energy onto this fluid because it's going to be drawing a suction, a fixed volume, positive displacement, a fixed volume is going to be moved no matter what happens. All right. The world could be ending around this pump. All right. And it will just continue to remove a volume, a fixed volume every time. Whereas a centrifugal pump is not self-priming. All right. If it's half filled with air, it will not run because there's nothing for it to impart a kinetic energy into. All right. Think about it. When we were looking at the centrifugal pump chart, we had pressure versus flow, right? And we turned off our valve. We closed the system off. We had a no flow scenario, right? We were not moving any gallons per minute. We only had a static pressure. All right. It's because we're not moving a fixed volume. We are at a fixed pressure. Everybody kind of understand the difference of what's happening here? All right, good. This is super major. All right. This is one of those things where knowing this is the matter of like looking like an idiot to your chief engineer one day. All right. This is one of those things where like, if you are like sitting there and you're like, I can't pump the bilge because, the pump isn't primed or I don't have the ability to grab a suction. He looks at you and he goes, it's a damn positive displacement pump. He'll say something else, or whatever pump name it is. And there might be more choice words there. But knowing the difference between these two pumps will allow you to physically pump a bilge, grab a suction, all right, pump a 55-gallon drum of oil and move it to one of your tanks without having to worry to prime it. All right, it will prime itself as long as it's dropped into the fluid. All right. So really quickly, this is the major difference. We're going to go back into this next class on Monday, but this is the big difference here on how our charts differ. And this is why I was saying, if you know these charts inside and out, you will know these pumps. All right. Look, we have constant flow. Our actual and our ideal are very close to each other. All right. We will always have the same flow when this thing goes on because it's going to have a fixed movement. All right. Everybody remember that whole, did anybody do this whole take place thing when they were in like kindergarten? They would move like a stick from one of their neighbors and then pick it up and put it on there. plate and they keep going like that. All right. It's the same idea if anybody had that same kindergarten experience that I did. You're basically moving the same amount of fluid no matter what happens. The same volume. As soon as you turn it on, boom, this thing is on, and it's going to be moving however many gallons per minute at that point. All right. So let's get ready for the quiz. It's a good place to stop. Now, let me see what's going on over in this world of our STCW stuff. Oh, is anybody able to get John Forrest on? Is he in?
Oh, he didn't answer my text.
You didn't?
No.
All right. By the way, I will be putting the pumps on as well for the PowerPoint, so you guys can look at those. Let me see. All right. So a couple of you have decided to take the test, but the quiz technically, but didn't do the STCW or the 540 lab agreement. All right. So like I said, I'm going to just start taking points off. You should get them in faster than you think. So check your STCW, check your 540. If you don't know what I'm talking about, ask a neighbor at this point. Look at the first classes on YouTube. All the information's there. All right. Like I said, yeah, to the end of the day on Friday. That's 3 days of this. It's a week. All right. So everybody here took the test, took the quiz. Get those lab agreements, get those things in. I'm going to just take off points and I don't know from where. It might be your first test. You have to do this. This isn't an option. Just because you don't sign it doesn't mean it's not going to pertain to you. All right. Before this quiz opens up, we have 3 minutes. Anybody have any last minute questions about piping? No?
Real quick, do we need to know the exact names for like pipe sizes? Like, do I need to remember that for the sample pipe sizes, like the wall is 0.216 and it's
No.
called STD? Okay.
You just have to know if it's a schedule 40, that's like a standard. And as you increase your schedule, the wall thickness is going to increase. That's really what you need to know.
But I don't need to know by how much it increases. Okay.
No, not at all. All right. Last thing I just want to show you guys before this opens up. Someone came to me with a question yesterday about schedule and everything like that. And I found this infographic that would help. All right, so take a look at, we have our NPS or nominal pipe size. All right, see how it's basically right in the middle? And anything below 12 inches, all right, for 12 inches, for 14 and above, it's going to be that outside diameter. For anything that's below 14, if we look at that PowerPoint again, all right, and this is real quick before the quiz opens up. Before, when we looked at it, and it was that 3-inch pipe, nothing on that drawing was 3 inches, correct? That outer diameter, inner diameter, that pipe wasn't technically 3 inches, right? So as we increased our schedule, we had a thicker and thicker wall thickness. But our inner diameter wasn't technically 3 inches, and our outer diameter didn't change at all. All right, so for NPS, for 14 and below, all right, so 13.99999 repeating and below is going to be the nominal pipe size. It's going to be that intermediary right below the surface. All right, so pretty much most people will consider it to be its outer diameter, but it's really not. All right, and if you're curious, go take a tape measure. Go measure piping down in your basement. I'm sure you'll have some sort of piece of pipe that you can measure, and it's not going to be exactly 2 inches. It'll be like 2.0125. All right. So, but it will be labeled as a 2-inch piece of pipe. So just take a look, and that is why it's showing. Okay. Other than that, You guys have everything that you need to know. The quiz should be open now. All right, again, I double checked that it should be good this time. There's no pictures. 2, once you're done, just leave quietly so everyone else has the same time as you to do this. All right.
Once we're finished, we can go, right? All right. Thank you. Have a nice day.
Mr. Callahan, I want to talk about like next week, if everybody's done with the test.
James is still taking it.
Oh.
All right. Everybody's done. So does somebody want to, is it
Yeah.
private?
I just gotta get Liberty for next week, Wednesday.
You have to do Liberty next week for next Wednesday?
Yeah, I was gonna ask you how you would be able to sign the Liberty forms.
What's it for? If you don't mind me asking.
It's really important. It's for my citizenship actually.
Then you're good.
So,
Just send it to me. I'll send it. I'll sign it via the computer.
PDF,
All right.
right?
Yep.
Okay.
Don't worry about it.
Thank you.
Yep. No problem. That's not going to be posted via YouTube, so you're going to have to. Oh, he's gone.
Yeah.
I'll take care of it later. What do you got?
So concerning the tweak card,
Okay.
so I tried to apply, but I haven't gotten my permanent residency first, so I'm still considered international.
Okay.
I don't know how I can work that out because I was supposed to have gotten my permanent residency card, but when I contacted immigration, they said things are going really slow because of COVID.
Mhm.
So far behind, so I don't know about that.
So you don't have your permanent residence. Where is your citizenship now?
Nigeria, West
Okay.
Africa.
Do you have I know I'm asking this because I know the Turkish students, they have an actual representative that they deal with, but they get their own license and everything. You're going after a U.S. license, right?
Correct.
Okay. Now, do you have like a representative at the school or anything like that, or are you just basically free flowing?
I really don't know if we have a representative because this is my first semester in Sunny. So I literally just came and I'm in the regiment program. So I'm still trying to get to know my way around.
Okay, so did you only complete the fall semester, or this is literally the spring is your first semester?
Yeah, the spring is my first semester.
Oh, okay. All right. So, all right. Are you now? Here's a couple questions for you. Are part of the regiment? Are you planning on coming up this semester in the fall?
Correct.
Okay. So you don't have to worry so much about getting on cruise with the TWA card. So that's not as a big deal. All right. If you were trying to get on cruise this summer, it would be a different story of what we would be talking about. Don't worry about.
Actually, I was planning on coming on cruise this summer.
That's the thing, is that you will be unable to. You're uneligible because you're not in the regiment. All right. Are you in JSTART?
Yeah, I'm in JSTART.
Okay. So you have a lead instructor and everything. You have lead 102, right?
Sure.
All right. Who is it?
That is Dawning.
Does it start with mate? Because that would be helpful.
Yes.
It is?
Yeah, and it's a lady. I think Ernest or something. Can't really remember.
Okay. So if she's a mate, be in communication with.
Yeah, because I remember in our last class, she talked about if